Okay, this is the lecture after the second quiz, so it will just be a 1-hour lecture. My plan is to do the makeup on the second quiz a week from Sunday on the same basis as the first one. So anyone who wants to take the makeup can expect to get it in the mail. After grading the quizzes, if there are any marginal cases, like someone got 15 and could get 16 if they took the makeup, I'll probably send an email asking, do you want to take the makeup? If you took the quiz and did less than 15, you'll certainly get the makeup. If you didn't take the quiz but have turned in homework, I'll assume you want it. If anyone hasn't been turning in homework and still wants a makeup quiz, better send me an email. My plan for tonight is to spend time on some homework problems that either caused some trouble last year or have caused some trouble this year, and many of these involve conditional expectation. I hope to convince you that conditional expectation, while you may still regard it as a pain, is the only way to get answers in a lot of questions. And that's nicely illustrated by the first one. This is a problem from the book, which I have called Tartan dice, because the problem in the book involves a 6-sided die where 3 of the faces have one tartan, 2 of the faces have a second tartan, and the remaining face has a third tartan. And the question is, what's the expected number of die rolls until you've rolled each tartan at least once? Yeah. It's a Scottish plaid. So I did the very simplest version of this a while back. Remember, this was the one where whenever someone registered for an extension course, with an equal probability of a third, they got a nice photo of Dean Mary Higgins, Dean Michael Schneegel, or Dean Henry Leitner emailed to them. And that was easy because the probabilities were the same as at every stage. The one from the book is hard because the probabilities are different at every stage, and I've invented an intermediate case to do in class. The plot line on this is that the Gender Equality Compliance Officer says that the extension school shouldn't be sending out twice as many photos of male deans as female deans. So to solve the problem, the deal is this. You register for a course, and you get Dean Mary Higgins with a probability of a half. Dean Michael Schneegel or Dean Henry Leitner, each with a probability of 1/4. So you have a 50% chance of getting a male dean, 50% chance of getting a female dean, but there are 3 possibilities in all. And the random variable x that we're interested in is, of course, the number of times you expect to have to, the number of times you register for a course, the number of registrations to get a full set. And just to make sure that everyone is in agreement with me about what x means, here's a sample outcome. You register for your first course, you're emailed a photo of Mary Higgins. The next time you get a Henry Leitner. The next time you get a Higgins again. Finally you get a Schneegel, and you have a complete set. So x has what value there? 4. And just one other one. Leitner, Leitner, Schneegel, Leitner, Schneegel, Higgins. That one has x equals 6. Now, I believe, though I've never tried, that it would be a real pain to work out the mass function for this random variable. That is, to figure all the different ways that you could get your third dean after 8 course registrations and add up the probabilities for each of them. But working out the expectation is much easier because at each stage of the process, you've got a random variable with a geometric distribution, don't you? you say at every stage, I've got 1 chance in 2, or 3 chances in 4, or 1 chance in 4 of getting a dean I don't already have. And you know in that case that the expected number of registrations in order to get a dean you don't already have is 1 over the probability of getting a desirable dean. So we can make a little diagram showing what's going on here. I hope I'm going to leave myself enough space. I think I'm going to put it up top just to be safe. So you start out, and there are 2 distinct cases. Either event H happens, and you get a Higgins, or the complement happens, and you get a Schneegel or a Leitner. And each of these will happen with a probability of 1/2. And you pursue different paths depending on what happens. If you get a Higgins, the rest is easy. If you get a Higgins, then you have to get 1 Leitner and 1 Schneegel. So you wait until you get either a Leitner or a Schneegel. Now you've only got 1 chance in 4 of getting the missing dean. You register for lots and lots of courses, and sooner or later you will get the missing dean. So that's the easy case. We'll be able to deal with that without too much trouble. It's the second case that's a little bit troublesome. In the second case, you have one of the male deans, so you've got 3 chances in 4 of getting a dean that you don't already have, and that's twice as likely to be Dean Higgins as it is to be the missing male dean. So this splits where you have an event that I will call H2, where you get your Higgins second, and H2 complement, where the second dean you get is the male dean you didn't have on the first try. And then to continue, now on this branch of the tree, you've got one of the male deans, you've got a Higgins, and you have to wait until you get the missing male dean. Here you now have both male deans, and you have to wait until you get a Higgins, and you're done. And I maintain that the only straightforward way to do this problem is in terms of conditional expectation, where you say there are 3 distinct cases. The case where I get a Higgins, the case where I get a non-Higgins followed by a Higgins, and the case where I get 2 male deans in succession. So let's work those out. The first one is fairly easy. The first one is where you start out with event H. You get a Higgins. The probability of getting a Higgins on the first try is, of course, 1/2. And then the probability, the expectation of X conditioned on having you got your Higgins is pretty easy. How many tries did it take you to get your Higgins? 1. Okay. Now you've got your Higgins. What's the probability of getting a dean that's not already in your collection? 1/2. So how many tries is it going to take to get a second dean that you don't already have? 2. Okay. Now you have every dean except either Leitner or Schneegel. You have a probability of 1/4 on each successive course registration of getting the missing dean. So how many courses do you have to register for on average in order to get the missing one? 4. So if you start with Higgins, which happens half the time, the expected number of course registrations to complete the set is 7. Now, let's try the second branch. The second branch is where you get a Higgins, where you get a non-Higgins, and you follow that up with a Higgins on your second try. Now, what's the probability of that? The first dean you get is one of the males, and then having got a male dean, the second different dean that you get is a Higgins. It's 1/2 for this, of course, because half the photos are of male deans. And now you have remaining one male dean, which shows up with probability 1 out of 4, Dean Higgins, who shows up with probability 2 out of 4, and one dean that doesn't count because you've already got his picture. So what's the probability the next new dean you get is a Higgins? 2/3. So we've got 1/2 times 2/3, or 1/3, and maybe we just better check that these sum to 1 before we go on. The probability that you start by not getting a Higgins and then proceed to get as your next dean another of the male deans, so you've got 2 male deans in a row, leaving only Higgins, is 1/2 for not getting a Higgins on the first try, times 1/3 for getting the missing male dean rather than the Higgins on the second try. That's 1/6. And sure enough, 1/2 times 1/3 times 1/6 equals 1. So the rule for conditional expectation, remember, is partition the sample space, find a set of disjoint events whose union is everything and whose probabilities sum to 1, and then multiply these probabilities by the expectation conditioned on what happened. Yes?
Can you just quickly explain, I understand where you got the probability of H to 1/2. Then when you move down to the next line, I'm not exactly sure what you're trying to find.
Oh, okay. What I'm trying to find is the probability of the event. The first dean you get is not Higgins,
Right.
and the second dean you get is Higgins.
Okay.
And I maintain the probability of that is the probability of getting a non-Higgins on your first try, which is 1/2, times the conditional probability, already having one of the male deans, of getting Higgins as your second new dean. Since the probability of getting a Higgins is twice as high as the probability of getting the other male dean, when you get your new dean, it's twice as likely to be Higgins as the other missing one. So that gives me 1/2 times 2/3. Yeah,
Why
Sue?
isn't it 1/2 times 1/2? Because
Yeah.
the second time you could get the first guy that you already got again, couldn't you?
But the question is, what I'm saying here, the event H2, let me make this very clear because I think I see what you misunderstood in my convention, Sue. The event H2 means after getting a male dean, the next dean you get that's different from the one you've already got, which may happen several registrations later, is Higgins. It's not the dean you get on the next registration. It's the next dean you get that's different from one you already own. Okay, so let's figure out, if we go down this route, what the expectation of x is. And x is now conditioned on the event H complement intersect H2. Okay. How many registrations to get your first dean? One. Okay. Now you've got one of the deans, and there's still 3 chances in 4 on any successive registration that you'll get a dean you don't already have, and therefore, what's the expected number of registrations to get a dean you don't already have? 4/3. Now, your second dean was a Higgins, so you now have one of the male deans and one Higgins. What's the probability at this point that when you register for a course, you'll get the one and only dean you don't already have? 1/4. 1/4, yeah. Right? Because it's a male dean, it's only 1 chance is in 4, and therefore, how many expected registrations for the third try where you get your final dean? 4. Okay. There are, by the way, a whole lot of ways to do this problem wrong, and I have discovered most of them. Okay. This was 19/3 when I worked it out before. Now the last case. The expectation of the total number of registrations conditioned on the first dean you get is not a Higgins, and then the second dean you get is not a Higgins either. So, amazingly, you get, let's say, a Schneegel, and then you may get some Schneegels mixed in, but the next Dean you get you don't already have in your collection is a Leitner, and you've got to finish things off by getting a Higgins. Okay? 1 for the first Dean, 4/3 again to get the second Dean, but now your missing Dean is a Higgins, so how many courses do you expect to have to register for? 2. Because you've got a probability 1/2 of getting a Higgins. That means the expectation of that geometric random variable is 2. And this one is 13/3. And now I can just add everything up. The expectation of x is the sum over all the different subcases that partition the event space of the probability of that subcase times the expectation of x given that subcase. So we've got 1/2 times 7 plus 1/3 times 19/3 plus 1/6 times 13/3. The lowest common denominator of these is 18, so we've got 63/18 plus 38/18 plus 13/18. And when you add those all up, you get 104/18. And if you're really good in factoring in your head, you can turn that into 19/3 or 6 1/3. I believe the answer to the one in the book, where you have probabilities 1/6, 1/3, and 1/2, is given as 7.3, and that's not an approximation. That answer in the book is exact as given. It just amazingly turns out that the fraction that you get has a 10 in the denominator, so 1 decimal place makes it exact. Questions about this rather difficult question? I debated this for a couple of hours with students last year when I assigned it, so I know that it's challenging. Catherine, you still look puzzled.
Yeah, I guess I don't really understand. I understand now where you got your numbers for probability of H, probability the H complement intersect H2, but I guess you're looking at 3 different paths and you're trying to figure out.
That's right. I'm looking at 3 different paths.
So why are you only calculating the probability of getting H on the first one and the second one then getting for 2?
Because the first path doesn't split after the first Dean, and the reason for that is that the probabilities are equal for S and L. Okay. I included that simplification to make the problem fit on this board. And in the homework, it will split more ways. In the homework, basically, there are 3 different Tartans. They all have different probabilities, and there are 6 different paths through, and you really have to work them all out.
Okay.
Other questions about this? Okay. The next problem I want to discuss is related to a problem on the upcoming homework involving a postman who on most days of the week may or may not put mail in your mailbox, but who on Thursday, as I recall, is guaranteed to put mail in your mailbox. And I've never seen a name for this distribution, so I have invented the name Terminated Geometric, which will identify it on the lecture video. I went through several iterations of this scenario before I got one that my wife regarded as sufficiently politically correct to publish. So the final deal is this. We have a young man named Blaise Pascal, and a revision of the No Child Left Behind Act says that any child of a famous mathematician is required to pass a test on probability theory in order to graduate from high school. And this is one of these tests where you can take it over and over and over again. And this kid is so-so. Given any test, he has a probability P of passing. Now, the person in the Department of Tests can calculate that she will have to write an expected number of tests equal to 1 over p, and if p is small, she may find that unacceptable. So she turns the law to her advantage and says, look, if this kid is faced with the prospect of taking his nth test, she's going to declare him learning disabled, lower the passing score to 0, and he's guaranteed to pass. So here's a case where we have a geometric distribution, except at some point everything stops. It's guaranteed to succeed. It's like having a die. You roll it over and over and over again, but it's rigged so that on the 10th try you get a 6 no matter what. And this now sounds like a very, very complicated sort of distribution to deal with. And in fact, it's remarkably easy if you use the tail sum theorem. So what we have is someone keeps taking tests. You pass a test with a probability p, fail with a probability q, which is of course equal to 1 minus p. And the kicker in this problem is that test n is an automatic pass. Okay. Let's recall the tail sum theorem.
Paul,
Yes?
can you try a different pen, please?
I just switched.
Okay.
Yep. See,
All right.
that one faded away to nothing. This brand works better than the others, so I'm going to try this before changing colors. So the expectation of the random variable x, which is the total number of tests, including the final pass, the tail sum theorem says the expectation of that random variable, since it's a random variable that assumes only integer values, is the sum from k equals 1 to infinity of the probability that the random variable has a value at least as large as k. You could also write this as the sum from k equals 0 to infinity of the probability that x is greater than k. They both come out the same. Now, I've written the sum as a sum up to infinity, but that's not really so in this problem. If k is greater than or equal to n, then the probability that x if k is greater than n, the probability that x is greater than or equal to k is equal to what? 0, right? Because there's no probability that this kid will have to take more than n tests. He will be passed on the nth test. So that means the upper limit is really n on this series. And up to n, we've just got a geometric series. So the expectation of this random variable is the sum from k equals 1 to n of the probability that the number of tests required will be at least k. How many tests does the kid have to fail in order to be asked to take his kth test? K minus 1. If I set j equal to k minus 1, I can write this as the sum from j equals 0 to n minus 1 of q to the j. And this is a sum we know how to do because it's an intermediate step in figuring out how to sum the geometric series. This is 1 minus q to the n over 1 minus q. So that's the answer. If you want to write it in terms of p, it's 1 minus p to the nth, divided not by q, but by p. In other words, if there were no stopping condition, if the kid just took tests forever and ever, the expected number of tests would be 1 over p. But this condition that on the nth test he passes automatically subtracts 1 minus p raised to the nth power from the numerator. And you can see 1 minus p is less than 1. If n gets very large, this doesn't make much of a difference in the expectation. I was sufficiently skeptical about this answer that I checked it. So a sanity check, let's suppose that n equals 3 and see if we get the right answer. For n equals 3, we can do it directly. The expectation of x is 1 times the probability that Monsieur Bayes will only have to take one test is, what's the probability that he passes on the first try? P. Or he may have to take 2 tests. What's the probability that he takes two tests because he fails the first and passes the second? Or he may take 3 tests, and if n equals 3, the deal is if he has to take a 3rd test, he's guaranteed to pass it. So what's the probability that he has to take 3 tests? Q squared. All he has to do is fail the first 2 tests. Okay. Now this is written in terms of Q's and P's, but if we write it out in terms of Q's, we get 1 minus Q for the first term plus 2Q minus 2Q squared from the second term plus 3Q squared from the third term, which is indeed 1 plus Q squared, which is, as advertised, 1 minus Q cubed divided by 1 minus Q, checking with that. So in a simple but not entirely trivial case, we get the right answer. Questions about this one? This was throwing people last year, but I think that it was because the book doesn't give the hint that you should use the tail sum theorem. Once you get the idea of using the tail sum theorem, it turns out to be remarkably easy. Okay, the next problem was suggested by email. This is the problem about the manager who has n pitchers in his bullpen. R of them throw only strikes, n minus R of them throw only balls, and he doesn't know which is which, so he keeps bringing one relief pitcher after another into the game until he finally gets one that throws only strikes. And the email I got said, I can get an answer to this in terms of a whole bunch of factorials. Is there any simpler way to do this? And then I saw on one of the homeworks as I was glancing through them, expectation. I can't see how on earth to do this. And I guess I should have given a bigger hint, because getting the expectation in this case is much easier than getting the mass function. But unless someone points out at least that it's very easy, you'll try to do it by summing all these quotients of binomial coefficients, and you will either become a great combinatorist or you will get nowhere. So here's the easy way to get the expectation.
You don't know which problem. This is one of the homework problems?
Yes. This is assignment 8, problem 4.
Thank you.
In the final game of the World Series, a baseball manager has N pitchers available in his bullpen. Of these, R will throw nothing but strikes, while the other N minus R will throw nothing but balls. Nobody knows which is which, of course. The manager brings pitchers into the game in a random order. The random variable X is the number of pitchers he must try before finding one who throws strikes. Find the probability mass function for X, which is the major issue I want to address, and calculate its expectation. Assume R is greater than 0, because the general formula you get is wrong if R equals 0. Now, here's the way you want to think about it. Line everyone up in the bullpen. Okay? We've got these N pitchers lined up in the bullpen, and R of them are the kind that throw strikes, and the other N minus R throw only balls. So this is R, S's, and N minus R, B's. Everyone see that? And they're arranged in a random order. The bullpen coach has just used some random number generator to bring them out in a random order. Now, the number of pitchers that the manager has to bring in before ones that get strikes is the number of pitchers in this first group plus the one who throws the strikes. But now if you look at these groups, here's one, here's one, here's one, here's one, here's one, here's one. Which of these groups has the greatest expectation? The bullpen coach has just unwittingly lined up someone who throws strikes. Now he's going to bring out more pitchers. The expected number of ball-throwing pitchers he will bring out before the next strike-throwing pitcher is independent of how many pitchers he's already called out, right? So each of these groups, that one, that one, that one, that one, that one, that one, have the same expectation.
Why is that? Does he repeat? Once he uses a pitcher, do they go back and he can pick?
No. They don't even have to come into the game. They're all lined up in a row.
Okay.
And secretly, they all have this B or S characteristic.
All right. Okay.
And now you ask, given two successive S pitchers, or the first S pitcher or the last pitcher, how large is the group of ball pitchers? And I maintain that each of those groups of ball pitchers has the same expected size. That is, that there's no basis to expect to find more ball-throwing pitchers between the first and second strike throwers than between the next to last and last, or between the last one and the end, or before the first one. And therefore, how many groups do we have? Be very careful. There are RSs.
R plus 1?
They're very good. They break the ball-throwing pitchers into R plus 1 groups. So we've got R plus 1 groups of Bs. And now we're more or less done. The average per group is, well, if you take N minus R Bs and break them up into R plus 1 groups, the expected size of a group is N minus R over R plus 1. And so the expected number of pitchers that the manager has to call is equal to 1. That's the guy that throws the strikes, plus N minus R over R plus 1, which is the expected number of ball-throwing pitchers that come in before the strike-throwing pitcher. And that simplifies quite nicely if you put it over a common denominator of R plus 1 to R plus 1 plus N minus R, or N plus 1 over r plus 1. There are lots and lots of very hard ways to do this problem, for which I apologize. If you try doing it in terms of binomial coefficients, you are likely to come to a dead end. So this is a nice illustration of a problem where you can figure out the expectation of a random variable fairly easily, in spite of the fact that it's hard to get at the mass function. It's not that it's hard to get at the mass function, because I'm about to do that, but that it is hard to calculate the expectation given the mass function.
Before you erase that,
yes.
Can I just ask one question? If the first pitcher or the last pitcher, or say both of them, are strike throwers,
then the first group or the last group has 0 members in it.
but it doesn't change my r plus 1.
It doesn't change the r plus 1. You have r plus 1 groups. Here, one of the r plus 1 groups right here in my example had size 0. Okay?
Yep.
Okay, now, the request to discuss this problem, though, prompted me to think about the following situation. I showed you, did I not, that the Poisson distribution is the limiting case of a binomial distribution. In the binomial distribution, there is a finite upper limit to the value of the random variable. But the Poisson distribution arises in a limiting case where that upper limit goes to infinity. And interestingly, the geometric distribution also arises as a limiting case, and I think I can explain that fairly easily to you in terms of blackjack. So this is also relevant to casino night for 2 weeks from now. One thing you might do for casino night is go on the internet and look at card counting strategies for blackjack. Unlike real casinos, our casino will allow people to bring all sorts of charts and tables, and as long as they don't delay things too much, even to take some time consulting these before placing their bets. Because the interesting thing about blackjack is that there are circumstances where the conditional expectation for a blackjack player is very slightly positive. And you can read all about this on the internet, but in a very simple form, here's how this works. It works to the advantage of the player to have lots of 10-point cards sitting in the undealt deck. The 10-point cards are 10s, jacks, queens, and kings. And there are a couple of reasons for this. One reason for it is if you get one of those 10-point cards and an ace, that's a blackjack, you get paid off at a rate of 3 for 2, whereas if the dealer gets one, you lose, but the dealer doesn't get anything extra. He just collects your bet. So the rules are sort of unsymmetrical, specifically favoring you in the case where you get a 10-point card and an ace. The more 10-point cards sitting around, the better your situation is. On the other hand, having lots of low cards remaining is disadvantageous to you, and 5s are particularly bad because if the dealer has a total of 16, he has to draw. And the one thing you don't want the dealer to draw under those circumstances is a 5, because that makes the dealer's total 21 and no one will beat him. So the original card counting systems basically figured 10-point cards are good for you to have left in the deck, 5s are bad for you to have in the deck. And when I first learned how to do this, I tried against a blackjack video game on a cruise ship where you could only bet a quarter. I made $5 last for 4 days, which I thought was pretty good. But the simple system I was using was one that I learned from the book, which was basically count the 10-point cards and count the 5s. And when you've seen lots of 10-point cards and very few 5s, place the minimum possible bet because the odds are against you. But if you get into a situation where lots of 5s have shown up and very few 10-point cards have shown up, then the odds have turned in your favor, and you should place as large a bet as the house rules will allow. Now, because I want to deal with a manageable problem, let's suppose we're just counting 5. So since this distribution is technically called negative hypergeometric, and since this is not quite 26 characters, I'll call this section negative hypergeometric. This is not in the notes, alas, but I hope to get a pretty good explanation of it on the board. Now, an interesting thing about blackjack is different places use different numbers of decks. Needless to say, the card counters prefer that a very small number of decks be used, because, for example, if the house is using only one deck and all 4 5s have shown up, then the player knows there's no chance that another 5 is going to show up. That looks really good. If, as is more traditional, the house uses 6 decks, then having most of the 5 show up is a much less likely event. So we can, in fact, consider 2 limiting cases where we're counting 5s. I'm going to use as my random variable x the number of cards until means it includes the card where the 5 shows up. The first 5 shows up. And here's one limiting case. Suppose you play blackjack, not merely with one deck, but just one suit. You take the 13 spades out of a deck. You got 13 spades, 1 ace, 1 2, 1 3, 1 4, 1 5. In that case, what's the probability that the 5 will show up first? You got 13 spades shuffled so they're arranged in a random order.
1/13.
1/13. What's the probability that the 5 will show up 7th? 1/13, right? You'll have an absolutely uniform distribution. So for one suit, the probability that x equals k is precisely 1/13 because the cards are arranged in random order, and this is true for all values of k for 1 up through and including 13. Now the other limiting case is where you have very many decks. You go to a casino and you suddenly discover they have bought 1,000 decks of cards and they've shoved them into this gigantic machine, and this will keep dealing blackjack for the rest of the year. Now, in that case, you might as well be rolling a 13-sided die every time. The fact that cards are coming out of the deck is essentially irrelevant. Each time a new card comes up, it has 1 chance in 13 of being a 5 and 12 chances in 13 of being something else. So what kind of distribution do you have there? Another way to achieve this would be every time you deal a card, you put it back in the deck and reshuffle. 1/13 each time for getting a 5. That's a geometric distribution, right? So in that limiting case, we also know the answer, but it's rather different. In that limiting case, the probability that the random variable x has the value k is equal to 12/13 raised to the k minus 1 power for the first k minus 1 cards, which are all non-5s, times 1/13 as the probability for getting the 5 on card k. Everyone comfortable with this? This is basically sampling without replacement, sampling with replacement, and these are 2 very simple cases. Now you can see there's a whole raft of intermediate cases. You can have 2 suits with 2 5s out of 36 cards, or you can have an entire deck with 4 5s out of 52 cards, or you could have 6 decks with 24 fives out of 312 cards, and those sort of interpolate between this limiting case where you get a uniform distribution and this limiting case where you get a geometric distribution. So I'm going to do one specific example. I'm going to do the case where you have just one deck, and with one deck you will get 4 fives in 52 cards. Now, this is basically a Munchkin problem. And in fact, to prove it's a Munchkin problem, I wrote a Munchkin problem on the homework. This is the first problem on the first of the new problem sets, but it really should have been the last problem for next week. So you probably want to work it fairly soon, even if you don't turn it in next week. And the way this problem works is there are 6 Munchkins in the bag, 4 plain, 2 chocolate, and Thomas pulls them out one at a time and eats them. That makes it unambiguous that this is sampling without replacement. You can't put back a chocolate Munchkin if you've eaten it. And the problem is to figure out the probability mass function for the number of the Munchkin where Thomas gets his first chocolate Munchkin, and the probability mass function for where he gets his second chocolate Munchkin. And it is not uniform, it's not geometric, but you will discover that it's quite simple, and if you add these two together, you get the probability that Thomas gets a chocolate Munchkin on any particular number Munchkin. Of course, that's independent of what number Munchkin you consider. The probability of pulling a chocolate Munchkin as your 4th Munchkin is 1 chance in 3, because 2 of the 6 Munchkins are chocolate, and there's 1 chance in 3 that there was a chocolate one in any position. Okay, let's do this one. On my 3rd try, I found a really simple way of doing this. So here's the kth card, and it has to be a 5. What's the probability that this specific card K will be a 5? We've shuffled the deck. I asked, before anything has been dealt, you count down K cards into the deck and peek at that card. What's the probability that it's a 5? 1/13. Okay. Now, there are K minus 1 cards on this side that were dealt before it, and there are 52 minus K cards over here that are still in the undealt deck. And if this is the first 5, where are all the 5s hiding?
52 minus K.
In the 52 minus K. All 3 remaining 5s are in the undealt deck. So we now say, fine. The individual outcomes are the 12 cards that show up before the 13th card, which is a 5. And the favorable outcomes, the ones that contribute to this event, are the ones where all those cards are non-5s. And therefore, we have to select K minus 1 cards, which are all X's. They're not 5s. Out of how many? How many non-5s are there in the deck?
48.
48. Very good, Katie. It took me about 10 minutes to realize that. So out of the 48 cards that are non-5s, we need to select K minus 1 cards to go over there before our first 5, and there are 48 choose K minus 1 ways of doing that. There are 51 cards left in the deck, excluding the 13th card. Excluding card K. How many ways are there of choosing K minus 1 cards out of the 51 remaining cards in the deck? 51 choose K minus 1. And that, folks, is the answer. It's a little bit more complicated if you start asking what's the probability that the third 5 appears at card K, but it's not really much harder. It's just a Munchkin problem. You say, over here, I need 2 of the additional 5s and K minus 3 of the non-5s. So basically, this problem yields to the same strategy that worked very nicely for Munchkins. But now I want to write it in a manner that suggests 2 ways of looking at this and saying, yeah, aha, this is reasonable in the limiting case. So the first way I'm going to rewrite this is as follows. I'm going to write out the factorials. The probability that x equals k is 1/13 times, now what have we got? 48 factorial divided by 49 minus k factorial times k minus 1 factorial, divided by the denominator, which is 51 factorial times 52 minus k factorial divided by k minus 1 factorial. The k minus 1 factorials cancel out, and what we are left with is 52 minus k times 51 minus k times 50 minus k divided by 51 times 50 times 49, all multiplied by 1/13. Okay. In fact, this is obvious. I mean, once you figure it out, you say, this is so obvious, I could have written this down if someone had shown me the formula. Here's why. 1/13 is for card K being a 5. Now, once you have that, there are well, it seemed obvious a couple of hours ago. Let me think about this. Yeah, it is obvious. Okay. Because the deal is all the 5s have to be on this side, right? So consider the first of the remaining 5s. There are 52 minus k places to put it over here, and that's out of 51 possible places, right? There are 51 other places in the deck for, let us say, the 5 of spades, and of those, 52 minus k are still compatible with this being the first 5. Now, there are still 50 other places to put the next 5, and 51 minus k of them are unoccupied slots over here that don't have a 5 in it. And for the last 5, there are 49 places to put it, of which 50 minus k are over on this side. So that's another completely different approach to the problem that leads to this answer. You get one of these factors for each of the 5s. And I think I've got 5 minutes left, do I? I've got 7 minutes left. I think rather than doing the limiting case of this, I will finally address this vexing coin tossing problem, which Robert sent me an email about, the one with the 19s in it, and show you the very slight fix that makes the book's answer correct, and 2 different ways of looking at it. So this is the next topic, which I will call coin tossing. And here's the deal on this. You toss a coin until it comes off heads. This is the random variable capital N, and then choose a random number x uniformly not in 1 up through 10 to the nth, but in 0 up through 10 to the nth minus 1, so that none of the numbers that you can choose have n digits. They all have, sorry, none of the numbers have more than n digits. They all have n or fewer digits in them. Okay. This problem, though it doesn't immediately strike you when you see it, leads to a wildly undefined expectation for the number you get. That is, the expected number that will be generated in this process is the sum, not of a series that just goes something like 1 plus 1 plus 1 plus 1 in the St. Petersburg problem, but when you write down the series, each term gets bigger and bigger than its predecessor. So let's see why. Let's calculate the value little n of the random variable capital N. So a head might come up on the first flip, the second flip, the third flip, the fourth flip, and so on. The probability that the number of flips has the value n is very easy to work out. What's the probability that your first head will come on your first coin flip?
1/2.
1/2. The next one?
1/4.
1/4, 1/8, 1/16, and so on. Okay? Now let's calculate the expected value of the random number given that it took n flips. Okay. If it took 1 flip, you're generating a number that's in the range 0 through 9. What's the expected value of a random variable that can have, with the same probability, any value between 0 and 9 inclusive? It's not quite 5. It's actually 4.5. But it's 5 less change, and I'm going to write it as 5 minus 1/2. Okay. If you're generating a random variable that's equally likely to have any integer value between 0 and 99, what's its expectation? 50 minus 1/2. Yeah, Sue's got the gimmick. And now the general rule is fairly obvious. If you're generating any number up through and including 999, what's its expected value? It's 500 minus 1/2. Okay, now, I said I was going to try to convince you that conditional expectation was useful. We can calculate the expectation of x by just taking the products of these things and summing them up, right? We're partitioning the event space depending on which number coin flip our first head comes on. And our expectation for x is equal to the sum over little n from 1 to infinity of the probability that the number of flips to get the head is little n multiplied by the expected value of x, given that that number of flips occurs. And this is 5/2 minus change. This one is 50/4 minus change. This one is 500 over 8 minus change. And when I add this all up, I get something just awful, because I get 5/2. Let's just look at the first terms. I multiply the numerator by 10 and the denominator by 2. So this is 5 times as large as that. What do I have to multiply 50/4 by to get 500/8? So the second term, the third term is roughly 25 times larger than the first term, and so on. So there is the infinite series that would define the expectation if it converged, but it diverges wildly. That's the simplest way to show the expectation is infinite. Now I've got 2 minutes left to get the mass function, and it's my impression that I just didn't understand the communications I'd got about this problem, that people had figured it out. It's just that I overlooked the error in the book. But with the 0 through 99 business, it's very easy. The probability that x equals k is the sum from the number of flips equal d to infinity. That is, if the number you want is 67, you have to wait until the case where you have 2 flips to get your head, because that's the first one that allows you to get 2-digit numbers, right? And the probability of getting your first head after n flips is 2 to the n. And then you have 10 to the n numbers, of which yours is 1. So the probability of getting your chosen number is 1 in 10 to the nth. And therefore, you have the sum from n equals d to infinity of 1 over 20 raised to the nth power. I'd like this sum to go from 0 to infinity, because then I can do it. So I'll pull out a 1 over 20 raised to the d power. And now I have the sum from, let's say, j equals 0 to infinity of 1 over 20 to the j. Everyone knows what that is, because that's a geometric series. This will give me 1 over 1 minus 1/20th. And I've got almost 0 seconds left, but this is 1/20th times 20 over 19. So this is, as advertised, 1 over 19 times 1 over 20 to the d minus 1 power, which is the answer given in the book. And the only mistake in the book is that they say the numbers run from 1 up through 10 to the nth rather than 0 up through 10 to the n minus 1. Otherwise, the answer is fine. And I may have run a bit over, but we're done. Thank you.